Hello, Chemistry 12. This is Mr. Chan, and today's video is talking about reaction kinetics and reaction rates introduction. Now, when we talk about reaction kinetics, we are focused on how reactions occur, and when we talk about reaction rates, we're generally talking about how fast a reaction proceeds. So that would be the reaction rates. Now, there are many different ways to measure the rate of a reaction, but generally what we use in chemistry is we take a look at the change in the moles over change in time. Now, the change in moles, this little delta, means change. And you folks have probably been exposed to this back in Chemistry 11, when we talked about endothermic and exothermic reactions. Remember, we had talked about delta H being a positive value, and delta H being a negative value. Now, generally in chemistry, we focus on the change in moles, but there are other ways to measure the rate of a reaction. In your Hebden text, what happens is if you take a look on page number 3, they do give you an example here of how you can measure the rate of a reaction other than using the moles. Now, if you take a look, it says the rate of the above reaction can be found by measuring any of at least 4 different properties or characteristics. Now, the first one that they talk about that you could use is a color change. Okay? The reason why you could do a color change is due to the fact that you notice here in the reaction, you are creating a blue color. Oopsie, you're creating a blue color. So in this case, you can measure the intensity of the blue color, and that would tell us the rate of a reaction. Back in Chemistry 11, we talked about something called Beer's Law. And if you were in Chemistry 11 honors, that should be hopefully a review for you. Another way that they talk about is the temperature change. It says, since the reaction is producing heat, the slope of a temperature versus time graph allows you to find the rate of the reaction. They also talk about pressure. As they said here, you're producing a pressure, producing NO2 gas, and so you can measure the temperature. Now, notice in these 3 characteristics, you are talking about a change in color intensity, or change in temperature, or change in pressure, but you notice all of those is a change in time. The last way that you can measure it is a mass change. They also have a mass change here, okay? So you can measure and change in mass, but the majority of times that when we talk about the change in rate of a reaction, we're focusing mainly on the change in moles. Now, when we calculate the change in moles, it all depends on the mole ratio. So for example here, okay, so let's get the pen here. So let's say we have here, come on, pen. So let's say we have 2H2 plus O2 would give you 2H2O. Now, when we take a look at this, let's say we arbitrarily chose a number. Let's say I chose 5 moles per second. The amount of oxygen here would be 2.5 moles per second. And here, for the amount of products of H2O, this would be 5 moles per second. Now, again, the reason why you have 5 to 2.5 to 5 is all based upon the mole ratio. Here I have 2 to 1 to 2. So my ratio here is 5 to 2.5 to 5, and 2.5 is exactly 1/2 of 5. Now, why did I choose 5 moles? Is because it was just an arbitrary number that I chose. Not only do you need to be aware of the mole ratio for reaction rates, but you should also be aware that the products and reactants are opposite. So in this case, I could say that this side on the reactants is the rate being used. used up. And here on this side, my products is the rate being produced. But one thing I would like you folks to be aware of is in this particular case, the rate that you have here are opposites. So as one is being used up, the other is being produced. Now, let me give you an example of a question that you might see as a typical homework question. It says, in the following equation, the rate of consumption of H2 was 0.35 moles per second. How many grams of NH3 would you produce? So in this particular case, the first thing you would do is when you write out your balanced equation, you have to balance out. So in this case, okay, so let's say I have N2 plus, I believe, 3H2 would give you 2NH3. So the first thing is you want to recognize you have mole ratios. So in this case, I gave you the mole ratio of H2 was 0.35 moles per second. So here for H2 is 3.5 moles per second. So if I were to use the mole ratio here, nitrogen divided by 3, nitrogen here would be 0.117 moles per second. And NH3, oopsie, 0.11667 times 2. This would be 0.2334 moles per second. Now, remember here, what you need to do is you need to recall, okay, what you need to recall is you need to follow mole ratio. Okay. Now, once I figured that out, so now if I need to focus on the NH3, that's what I have here. Okay. So if I change that, so if I take the 0.2334 moles per second of NH3, I would need to multiply that by 60 seconds for over 1 minute. And then I would need to multiply it by nitrogen is 14, so 17 grams per mole, which is the molar mass. I cancel out my units here, seconds, moles. And what I get is an answer here is times 60 times 17. So that would give me here 238 grams per minute. Now that's my rate. And then I would multiply it by 10 minutes. And that would give me an answer times 10. So that would give me, in this particular case, 2,380 grams produced in 10 minutes. So in this particular case, you not only had to follow the mole ratio to figure out the 0.234 moles per second was produced, you had to change that into grams per minute, and then you multiply it by the 10 minutes to give you the mass produced in 10 minutes. Okay. hopefully this is pretty straightforward. Now, when we talk about reaction rates, one can use chemical equations to predict the relative rates of reactions. Now, when you take a look at this, the reaction between ions to form precipitates is generally fast. Why? Is because it involves only the simple attraction between ions in the solution. So in this particular case, if we take a look at a double replacement reaction, you have silver nitrate plus sodium chloride gives you silver chloride and sodium nitrate. This was a chemistry 11 double replacement reaction. If we take a look at the ions, here, the nitrate and the sodium would form one product. Here, the silver and chlorine would form the other product. In this particular case, this is generally fast. Generally fast because the ions are attracted to each other. And as a result, okay, there's nothing that is a simple attraction. Conversely, if you take a look at reaction between molecules, the reaction between molecules are generally slower. Why? Because the reactant particles need to have their bonds broken before a reaction can occur. Now, if you take a look at this, this goes back to when you were in chemistry 11, Lewis dot structures. So if we looked at hydrogen here, so hydrogen would be hydrogen, 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 hydrogen. Oxygen would be O double bond O, and water would be HOH. So notice in this particular case, the hydrogens and the oxygens need to have bonds broken. Before reaction. RxN is reaction. And in this particular case, you would notice in your here is you have new bonds formed. So because of the fact that you have to break bonds before new bonds are formed, it does take a little bit more time. Compare that to when I talked about the ions. The ions, what happens is that it's just simple attraction. There's no breaking of bonds. There's no reforming of new bonds. It's just coming together and getting your new product. Now, an example you could think of it is like this. When I take a look at the reactions between ions to form a precipitate, you could think of that as almost like dating. So you could think of it is when you like somebody and somebody likes you, if you're not attached, simple attraction for you folks to form a couple is a lot more straightforward and generally a lot faster. This particular scenario would be like if you were interested in somebody, but you were already dating somebody. What you would need to do to be honorable is you would need to break up with your current partner before you're able to, pursue a new relationship. So it does take a little bit longer. Okay, so reaction between molecules is like having to break up a old relationship first before you can start a new one. Now, when we talk about reactions, we can take a look at the phases of the reactions, and that could also tell us the speed of a reaction. So the speed of reactions is also based on the phases of the reactants. So you can have the solids here. Okay, so you can have the solids. They are generally the slowest reaction. And what you have is ions in solution is generally the fastest. Why are ions in solution the fastest? Again, it goes back to the fact that they have simple attraction. And as a result, there's no bonds that need to be broken. They're generally faster. Why are solids the slowest? About kinetic molecular theory, the solids have the particles are moving the slowest, so therefore the slowest reaction. Another term that you should be familiar with that we'll be using is the words homogeneous versus heterogeneous. Homogeneous means that the reactants are in the same phase. Okay, heterogeneous is when the reactants are in different phases. You folks probably remember this when you were in grade 11 or grade 10 when you talked about homogeneous mixture or heterogeneous mixture, where homogeneous is everything looks exactly the same, where heterogeneous you are able to see the differences. Again, if we were to take a look at the human race, we are called the Homo sapiens because of the fact that genetically we are all exactly the same. All right. So that is the first lesson of reaction rates. Please make sure to, if you have any questions, to come see me during flex time or during lunchtime. And do make sure, if you did miss my class, to come and see me to see what homework I had assigned to sort of cover this unit. All right. Thank you very much. Have a great day. Bye-bye.